Hey folks, and so the second part of our lecture is going to follow some of the math around momentum conservation. And so the story here is as follows. Two friends, Emma and Tom, are at rest on their perfect skateboards, which are able to roll freely without resistance 1.5 meters apart. Emma, who was holding a 5-kilogram ball when they were at rest, throws the ball horizontally to Tom at 12 meters per second. What are the velocities of Emma and Tom after throwing and catching the ball, respectively? Note, the masses of Emma and Tom are 55 kilograms and 80 kilograms, respectively, and assume there is no air resistance. So I'm just going to draw a diagram of what's going on in this problem. So initially, we have Emma holding a ball. Please pretend like this square shape is a ball. I messed up drawing that, and I apologize for that. And they're standing stationary in this initial scenario, which means that there's no movement or no motion. And remember that the momentum equation is P equals to mv, so if nothing's moving, momentum is 0. Now what's interesting is that there's an intermediary step where Emma throws the ball towards Tom, and conceptually speaking, there is no external force causing a velocity to happen in this problem, which means that the momentum is conserved. So the momentum is conserved in this intermediary step. And then when Tom catches the ball, Emma is still moving to the left, and then Tom starts moving to the right. And again, in this situation, momentum of the system is conserved because no external force is applying any disturbance to the system, causing something to move. Now, momentum conservation laws state that initial momentum is equal to the final momentum. Using definition of momentum is that we have momentum initial, velocity initial would mean that momentum final is equal to velocity final. So initially, what is being done in this problem is that Emma is throwing the ball towards Tom, but the question that is really asking us to find the velocity of Emma and the velocity of Tom at the step where Tom has caught the ball and is starting to move to the right. So in order to do that, we have to compute the intermediary step. So between this and this scenario, we're going to calculate the conservation of momentum. And in this scenario, initially, the momentum is 0. Now, because momentum is conserved, the total momentum of this scenario will be 0, but it will be expressed via the following equation, where we have the addition of Emma's mass and her velocity, and then the mass of the ball and the velocity of the ball. Now, Emma is 50 kilograms in mass. We do not know her velocity. We do know the mass of the ball at 5, and we do know the velocity of the ball at 12 meters per second. Now, plugging all those numbers in, down here, we have 0 is equal to 50 VE plus 5 times 12, which then means that VE is equal to negative 60 over 50, and it's equal to negative 109 meters per second. Notice the minus sign here. That's very important. In momentum conservation problems, the sign of your velocity tells you which direction an object is moving. Positive to the right, negative to the left, assuming you define your axis to be positive to the right. And I have not yet seen a convention where anyone chose anything different when it comes to writing problem sets. And so Emma's velocity is negative 1.09 meters per second. We found out this intermediary step, and then we also found out an answer to part of the problem, which is the velocity of Emma. Now, we need to calculate the velocity of Tom, and to do that, we're going to compare the momentum conservation between this scenario and this scenario. So again, in both cases, total momentum is 0, no external forces altering anything like that. And so in this scenario, we have a mass of ball times the velocity of the ball, which means we're focusing on this system, these two parts of the system, and how they end up affecting this final scenario, we have, again, from this initial arrangement, the mass of the ball times the velocity of the ball, which would equal to the momentum in this scenario, where we have the mass of the ball, mass of Robert, times the velocity of the Robert ball system. So plugging numbers in, mass is 5 kilograms, velocity is 12 meters per second, which is going to equal to the mass of Robert plus the mass of ball times that final system. And plugging everything in and solving means that the final velocity is going to be 0.71 meters per second of Robert and the ball. Notice how in this situation, the momentum conservation, we first focused on these two folks because Robert was just stationary there by himself, so he had no contributions to the momentum. And then for the second part of the problem, we focused on this system here because we already knew what was going on with Emma. Her situation does not change from one frame to another. And the only systems we wanted to look at was that of the ball and Robert. And I think this is a pretty good problem because it demonstrates this sort of sometimes selective thinking you would need to have on physics, quizzes and exams. Sometimes you don't have to look at the whole system. You can just do it more piecewise.